Now, obviously, our notion of error between forward and backward differencing is exactly the same. Yeah, so in the end, this method is still quadratic locally and linear globally. Yeah, but just an identical argument, and nothing's changed. But what has changed is the stability. This is actually a little bit surprising. So, again, remember that our model equation is y prime equals ay. But now our iteration scheme is a little bit different. In particular, assuming that I did this right in my notes, right, we now just have that. Yeah? Oh, there's a minus sign, right? Because, oh, no, there's not. Okay. Right, so all I did is say, okay, now that rather than evaluating the derivative of yk, I'm going to evaluate him at yk plus 1. Cool? So let's solve this from yk plus 1. So if we subtract this term from both sides, then you get 1 minus a h times yk plus 1 equals yk, or in particular, yk plus 1 equals 1 over ah1 minus ah yk. Yeah? Well, now first of all, this is like kind of interesting, right? We have two different formulas for yk plus 1 that are both just multiplied by a constant, but our constant is different. Right? So somehow these two different models for ODE integration are going to give us different predictions of the solution, regardless of whether they're stable or not. But now, if we want to check whether backward Euler is stable, we need to check when this number is less than 1, right? So in particular, when 1 over mod 1 plus ah less than 1. Yeah? Yes. So in particular, if we take the reciprocal of both sides, then we know 1 plus ah, that, now the inequality flips, greater than 1. Right? And now we apply our same proof from before. Right? That's minus 1 is less than 1 plus ah is less than 1. Then we subtract 1 from both sides, minus 2 less than ah less than 1. Oh, oops, this is completely wrong. I've got to catch me. Okay, this number has to be greater than 1. So, in particular, this means that 1 plus ah is greater than 1, or 1 plus ah is less than negative 1. Sorry, this inequality is always killing. But thankfully, from here on out, it's not so bad. So if we extend this one, right, this says ah is greater than 0, which is wrong here. What?
Should that be 1 minus?
Oh, that should be 1. Yep. Wow, I'm doing it all wrong. Sorry, guys. It's been a tough week. Yes, okay. Which says that h is greater than 0. Not entirely exciting. Yeah. And in the second case, this says, okay, ah minus is less than minus 2. Right? And if I divide by a, right, so if I multiply both sides by minus 1, the equality flips 1. If I divide by a, the inequality flips again because a is negative. Right? So this says that h is less than or equal to 2 over a. Right? So can this, and remember that this is an or. Okay? So we need to satisfy one of two conditions. Either h is positive, or I don't even care what. Yeah? In particular, for any positive time step, my ODE solver, this backward Euler method, despite my many proof mistakes, is stable. Hopefully I haven't totally confused you guys. Right? So this is great, because if I solve a stiff ODE using backward Euler, then no matter how big a time step I take, at least my solution won't explode. But something that you should keep in mind is that this has nothing to do with the accuracy of the solution that you get out of your solver. Right? So if I take like a time step of 4 bajillion, right? Like maybe I move from like the Paleolithic era to the time when the sun consumes the earth, I can do that with backward Euler, and I'll get a stable solution. In fact, I'll probably get 0 for almost any ODE I care about. But that doesn't mean that that solution has anything to do with what actually happens with my solver, because I took a time step that was unrealistic. Right? But at least it didn't explode. And that's what we can say about backward Euler. So when we're solving these systems, for example, another example of a stiff equation would be a cloth simulation, where cloth has some modes where it's bending and it's not, cloth is happy to bend and very unhappy to stretch, right? And so it's very stiff because the bending mode is perfectly happy to just do its thing, but the second that I yank it kind of laterally, the cloth is going to pull right back, right? So oftentimes cloth simulators will use methods like backward Euler. Maybe next week we'll discuss one of the famous papers. And the nice thing about that is that even if your cloth looks a little bit damped out, right? So backward Euler is going to just kind of get rid of these high frequencies. At least your cloth didn't grow to like 9 times its size and take over your computer. Yeah. So anyway, we'll conclude with just one example of a slightly more complicated ODE you could solve with forward and backward Euler, just to give you a sense of what these formulas look like. And so let's say that I wanted to solve y prime equals ay, but now y is a vector and a is a matrix. Yeah. Then what do forward and backward Euler give us? Well, forward Euler is pretty clear, right? Because you still just add a little bit of your derivative to yk to get yk plus 1. And if you do backward Euler and you work it out, now you're going to have to solve a linear system. So maybe we'll write down that really quick, and then we'll call it a day. And in fact, we are neither early nor late. So if we have y prime equals a y, like that, right? Then what was our backward Euler formula? Well, I guess we have it right over here, right? We have yk plus 1 equals yk plus, and now what? H times A, which is a matrix now, times yk plus 1. Yeah? So this is our model for backward Euler, and in this case, now it's solvable. Yeah? Because we move the A to the left-hand side, right? So you have the identity matrix minus HA yk plus 1 equals yk. And inverting this gives you the formula up here. Okay? So in other words, what did we show? Well, we showed that the spectral radius of this matrix is less than 1, by the way. But we also showed that if you integrate things forward in time, right? What's our trade-off? Well, forward Euler is not necessarily stable unless you use an itty-bitty time step. So you're going to do a lot of time steps, but each time step is very easy, right? It's just matrix multiplication. If you do backward Euler, each time step you're going to have to invert this matrix here, right? And chances are, if your system isn't linear, it's going to be a different matrix each time that you're going to have to factor, right? So your trade-off is you can take large time steps and potentially, predict things very far into the future, stably using backward Euler. But you're going to have to do more work per iteration if you want the same degree of accuracy, by the way. Or with forward Euler, you can get good accuracy, the same accuracy as backward Euler, but you're going to use small time steps to guarantee that your solution doesn't screw up. Cool. All right, so we'll stop there for today. Next time we're going to talk about higher order methods for integrating ODEs, and then we're going to dive into the case in particular of f equals ma, and understand what it means to simulate velocities, accelerations, and positions all at the same time. Then next week we'll talk about like heat equation and wave equation and all of our favorite model PDEs. Cool, so if somebody could hit the camera, we'll call it a day. And remember, your homework is due midnight tonight.